So far we focused the discussion on P0 and ways to handle it. We now turn to present an alternative to it that will serve us better. As we have just said, P0 has been our primary goal. With a lot of effort, we were able to analyze it theoretically, showing that a unique solution to this problem can be claimed if it is sparse enough. We also found a series of numerical methods to practically find this solution, and even accompanied these algorithms with guarantees for success. So the following question might surprise you, as we are about to question the very foundation of our discussion, putting a big question mark on P0. Is P0 really the proper objective to handle? Why should we question P0? Well, because it has some fundamental flaws, as we are about to describe. Already in the introduction of the problem P0, we mentioned some difficulties with it. Specifically, the equality constraint seems to be too strict. Let us demonstrate this. Imagine that a system AX equals B naught has a sparse solution. Now, as happens typically in signal processing, rather than getting B naught, you get a slightly modified version of it, B, contaminated by noise. You could even assume that the noise itself is of very small energy, implying that the signal-to-noise ratio is 1000. Searching now a sparse solution to the system AX equals B, we are likely to get only dense solutions. This sensitivity to negligible noise is troubling, to say the least. And if this is not enough, the L0 measure is also too strict, and for similar reasons. If a vector x0 is sparse and you add a negligible random noise to it, the L0 measure will consider the new version as dense. These sensitivities to small perturbations are unacceptable. What can we do? The answer is relaxation, changing the constraint from an exact equality to an approximate one. The new constraint states that AX should be epsilon close to B. Epsilon itself is a parameter that has to do with the deviations we expect. This modification clearly fixes the issue of the perturbations in B, since then the noise in B will be absorbed by the residual vector AX minus B, allowing for a sparse solution to remain feasible. What about the other problem? The tendency of L0 to be too strict? In fact, the proposed modification takes care of this as well. Assume that x0 is sparse and satisfies the equation AX0 equals B. We consider a perturbed version of it, x0 plus epsilon u. Plugging this noisy vector x into the new constraint, we get that it is satisfied as well if the norm of A times u is smaller than 1. Thus, a perturbation over the vector x is also absorbed by the constraint, leading to a sparse solution x0. On top of the obvious benefits just mentioned, moving from P0 to its approximate version, P0 epsilon, has several other advantages. For example, if the matrix A is square and invertible, obviously P0 has no meaning because AX equals B leads to a unique solution, regardless of the L0 penalty. On the other hand, the P0 epsilon problem remains relevant, as it may seek to deviate AX from B in an attempt to find a sparser solution. Indeed, more broadly, the migration from P0 to P0 epsilon means sparser solutions. This is easily seen by observing that the feasible set, the X's that obey the constraint, has grown, thus giving more freedom to the vector X to have a deeper sparsity. Another benefit of P0 epsilon is its ability to cope with a model mismatch. In fact, this is not a new property, but rather a restatement of our earlier claims about the ability to handle perturbations. When deploying our sparsity theory to signal processing, we assume that the given signal is a sparse composition of atoms from a given dictionary A. However, signals are rarely obeying such an exact model assumption. P0 epsilon can cope with this easily, considering the model mismatch as a perturbation. Therefore, P0 epsilon is more practical for our later signal processing needs. Last, but definitely not least, P0 epsilon could be perceived as a denoising algorithm. Assume that the vector B0 is a clean signal, being equal to A times x0, where x0 is sparse. We measure the vector B, a noisy version of B0, and our goal is to recover the clean signal from its noisy version. P0 epsilon is doing exactly that. Given B, it seeks the sparsest explanation to this vector in terms of a linear combination of as few as possible columns from A. If epsilon is set to the true noise level, then x0 itself is a feasible solution to the P0 epsilon problem. Indeed, if P0 epsilon leads to a solution of the same support as x0, a substantial decay in the noise energy will be obtained, thus qualifying this method to the name Denoiser. Great! We have a new and far better behaving definition for our goal, the problem P0 epsilon. What should we do about it? Well, everything that we did for P0 should now be upgraded to the new form. More specifically, we would like to analyze terms for getting a unique solution for this problem, identify pursuit algorithms that aim to approximate its solution, and maybe even come up with theoretical guarantees for their success. And yes, we will do all these. We will start with the easiest task of developing pursuit algorithms.